Hello everyone, this is a lesson on valence shells. We've been learning about what the atom looks like and that there's a nucleus and then there's electrons that are around the nucleus, and those electrons, according to Niels Bohr, exist at different energy levels, and we can draw that like this so that each the electrons are on different energy shells. Okay, so there's no actual shells around the nucleus, but this is a good way of describing what the atom is like. Okay, and so these electrons here, this electron pair, is at a lower energy level than these electrons on the second shell. So this atom with 23 protons has 2 electrons on the first shell, 8 on the second shell, 8 on the third shell, and then 1, 2, 3, 4, 5 electrons on the outer shell. So 5 valence electrons on the valence shell. And the reason that's important is because the valence electrons are the ones that are involved in chemical reactions, and we'll learn about that more in this unit. So Niels Bohr stated that the electrons exist around the nucleus at different energy levels. And the outer shell, the outer level, is called the valence shell. Okay, so the electrons on the valence shell we call valence electrons. So this atom here has 1 valence electron. So this is potassium, element number 19. Okay, 19 protons and 19 electrons. Okay, but only one of those is a valence electron. So the question that I want you to think about, what ion do you think potassium will form? Will it become a -3 or a +4 or a -2? Well, if you look at the periodic table, you can see that potassium, K, it's called, the symbol is K, forms a +1. Why does it form a +1? Well, what happens with atoms is they will become more stable if they have a full valence shell. So potassium has 1 electron on its valence shell. So if it's going to become more stable, it can either fill up this valence shell with electrons, or it could lose this one. So this now becomes its valence shell. That's a good option because it is empty, or it's full. Okay, so they're more stable when they're full. So potassium has 2 options. Fill up the 4th shell, or just lose that one so that the 3rd shell becomes the full valence shell. So how many electrons would potassium need to gain in order to fill up this 4th shell? Well, the 4th shell can hold 18 electrons. So potassium's not going to gain 17 electrons. It's much easier to just lose this one. And if it loses an electron, will it become +1 or -1? Well, it'll become +1. Okay? Why? Because now it still has 19 protons, but it only has 18 electrons. So 19 pluses and 18 negatives. Okay, so it's got 1 more positive than negative. So the overall charge of this thing now is +1. So potassium will become +1 because it will lose 1 electron, and this will give it a full valence shell. And as we just talked about, atoms are more stable when they have a full valence shell. Okay? So, excuse me. Which atom has a similar Bohr model diagram to a potassium ion? Here's potassium, element number 19. Still has 19 protons, but now it has an electron arrangement of 288. So which other element has an electron arrangement like 288? If you look on the periodic table, that would be over here. We got 2, 8, 8. That is argon. There it is, element number 18. 2 on the first shell, 8 on the second shell, 8 on the third shell. So potassium normally would be 2881, but when it loses an electron, like in a chemical reaction, then it becomes +1, and it's only 288, like argon. Okay, so when potassium becomes K plus 1, then it gains the same electron arrangement as the noble gas, argon. Okay. This one is selenium. So this is a new atom, a new element, element number 34, 34 protons, has 4 shells. It's on the 4th row. First shell is 2, then 8, then 8. And then selenium has 16 electrons. Okay, so a number of pairs and then 2 singles. So now, what ion do you think selenium will form? Remember, they're more stable when they have a full valence shell. So it has 2 options. It could gain 2, and that would fill this up, or it could lose 16, and then the third shell could become its valence shell. So is it more likely to gain 2 or lose 16? Well, it'll gain 2 electrons. And if it gains 2 electrons, now it has 34 protons and actually 36 electrons. And because electrons are negative, the overall charge now is -2. So selenium will become -2 because it will gain 2 electrons. And that will give it a full valence shell. Yeah? So the ones on the left side of the periodic table, they become positive because they are losing electrons. The ones on the right side of the table will gain electrons and become negative. Which atom has a similar Bohr model diagram to a selenium ion? Here's selenium, becomes -2. Which atom has a similar arrangement? Well, that would be 2, 8, 8, 18. And that is going to be like 2, 8, 8, 18. That's going to be like krypton, right? Selenium gains 2 electrons to become like krypton. So krypton's number 36, and it is 2, 8, 8, 18, like a selenium ion. Okay, so when selenium becomes an ion, Se-2, then it gains the same electron arrangement as the noble gas, krypton. So they're all trying to become like the noble gases. Okay, we call that noble gas stability. Okay, they are more stable when they have a full shell, like the noble gases. Okay, also what I'd like you to know are 4 periodic trends. So there are 4 trends that we can see in the periodic table. Some of them are kind of obvious and some are a little less obvious. So here's one. Atoms in the oh dear, tea time. Number 1, atoms in the same group have the same valence shell arrangement. Here's lithium and sodium and potassium. They're all alkali metals. And it says here, if they're in the same group, they have the same valence shell arrangement. Well, what do you notice about their valence shell arrangement? They'll have 1 valence electron. Okay, what about the alkaline earth metals here? Second, they would all have 2 valence electrons. What about over here, the noble gases? Well, they will all have full valence shells. And the halogens? They're all just missing 1, right? Fluorine has 7. If it gains 1, it has 8. Chlorine has 7. If it gains 1, it becomes like argon, has 8. Bromine is missing 1, it has 17. Okay, so the halogens are all missing 1 electron. Trend number 2. As we move down a column in the periodic table, the atoms get bigger. What? Look at that. Small, medium, large. And that's not even down to francium yet. Okay, so they are getting larger. We are adding shells. Okay, so go down the column, they get bigger. That's pretty easy to remember, I think. Trend number 3. As we move across a row, as we move across a period, the atoms have the same number of shells. Here is our old pal sodium. Here's magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, and argon. Okay, so as we move across a row, the atoms have the same number of shells. Yeah, they're all going to have 3 shells. Next period, next row, they will all have 4 shells. Now I drew them out like this so that hopefully you can see trend number 4. Trend number 4, as we move across a row, the atoms get, you can shout it out, maybe don't shout it out, the atoms get smaller. Look at that. We're moving across and they get smaller. Now that's kind of weird. Trend number 4 is a bit of a weird trend. Why are they getting smaller? I mean, this one here has fewer protons and fewer electrons than this one. Right? As we go across, we're adding protons and electrons. We're adding more stuff to them. Why are they getting smaller? Any guesses? The reason is because what we are adding is positive and negative charge. Okay? There's more positive charge as we move along because we're adding more protons to the nucleus. And if we're adding more protons, that's going to pull those electrons in closer. Okay? We're adding more protons and electrons. We're not adding more shells. So those electrons are on the same shell and the pull from the nucleus is getting stronger and stronger and stronger. And so the atoms get smaller. Okay, so this is because although we are adding electrons, we aren't adding new shells. We are, however, adding more protons, and so the pull on the outer shell is getting stronger. Okay, think about if these were magnets. Okay, the magnetic pull at the nucleus is getting stronger and stronger, and so those electrons are getting pulled in more. Okay, so hopefully that makes sense for trend number 4. Okay, last couple things I want you to think about. Here is potassium. Okay, it's got 19 protons, 19 electrons. Here's sodium, 11 of each. If you put sodium in water, it will zip around on the top and it'll react pretty strongly. You put potassium in, it'll zip around on the top and maybe catch on fire. You put rubidium in there and it'll practically explode. Okay, don't even get me started on francium. Okay, the further down you go, the stronger they react. So my question is, why might potassium be more reactive than sodium? Okay, why might potassium be more likely to react and give up this electron than sodium would be to give up this electron? Okay, well, the reason for that is potassium's outer electron is further away from the nucleus, so it is easier to lose that. So it's going to react more readily than this one. This electron's closer to the nucleus, so the nucleus can actually hold on to it better than potassium can. Okay, remember they're gaining or losing electrons in chemical reactions. Okay, what about on the other side of the periodic table? Here's fluorine right there. Here is chlorine. Remember, the halogens are highly reactive nonmetals. Why might fluorine be more reactive than chlorine? Okay, they are all missing one electron in their valence shell. Okay, so here's fluorine, here's chlorine. Why might fluorine pick up an extra electron faster than chlorine would? Any guesses? Well, fluorine's outer ring is closer to the nucleus, and so the nucleus is better able to attract one more electron than chlorine, right? This outer shell is further away, and so it's harder for the nucleus to attract more electrons. So I hope that that all kind of makes sense and that you understand the basic ideas. Valence shell is the outer shell. Those electrons are the ones that are involved in chemical reactions. And that is what you need to know for valence shells. Have a great day.